Hello students, and welcome to our lesson on functions. Functions are essentially everything that college algebra is about. I actually tend to refer to it as a class where all you do is learn about functions and how they relate to each other, what you can do with functions. And so this lesson is especially important because it really just sets the groundwork for everything that's going to happen in college algebra. So it doesn't really talk too much about the algebra skills themselves, but it is going to talk a lot about the notation that we need. So first, what is a function? So a mathematical relation between two quantities is often represented by the letters x and y. So you might have seen something like y equals x squared, y equals x cubed, things like that. Those are all functions. Generally speaking, we are going to replace the letter y with the notion of f of x, which we'll talk about a little bit later. But for now, we're just going to leave it as x and y, inputs and outputs. And generally speaking, the idea of a function is that you input one number and you output a different number. So in real life, we have a lot of things that work like functions. Usually vending machines are the easiest example, where you put in your dollar, you push a button, and then your snack comes out. And so the machine is the function that's taking in the input, which is the push of the button, and outputting the snack, which is the thing you desired, hopefully. So we have a lot of things in real life that work like functions, and we just want to be able to use mathematical notation to describe these things. And then we have one rule that comes along with it. So let's see what that is. If the relation, by the way, a relation is anything that inputs and outputs numbers or any objects, I suppose. But a function is a special type of relation, and that's what we're about to describe. So if the relation is a function, then each input corresponds with exactly one output. So now, what does that really mean? We can make it a lot easier to understand by thinking about x values as people, such as yourself or any of your friends, anybody you've ever met, and y values as their birthdays. So now how does that help? Well, it says that each input corresponds with exactly one output. So every person, okay, because people are the input, so every person has one birthday, where birthdays are the output. Okay, so in here, I'm just going to label real quick that birthday, that's the output, and person, that's the input. So you cannot have a person that has more than one birthday because you were born in a specific time and that time was on a specific day. Okay, at least most of us are not born twice. So every person has one birthday. Notice though that if you go the other direction, this doesn't have to be true. So if you pick a birthday, let's just say June 22nd, there are a lot of people that have that birthday. So it is not true that every output has exactly one input. It's only true, or it only needs to be true, if we go the other way. Every input has to have exactly one output. Each person is only allowed to have one birthday. If I ask you what your birthday is, you should not have to think about it. You should be able to just immediately tell me what that day is. All right, so now relations and functions can be illustrated using a graph. Okay, so sometimes we will see them the way number 1 through 4 look, where we're just seeing a bunch of coordinates. And then 5 through 7, we're going to see graphs. And then down below that, for 8 through 10, we're going to see them as equations or rules. But in order to test, because what we're about to be doing is test if these are functions or not. So in order to test if a graph is a function, we're going to check if it passes the vertical line test. And what we're going to learn in this is that passing the vertical line test means the exact same thing as every input corresponding to exactly one output. Those are the same definition. It's just visually, all we have to do is draw a vertical line to check. All right, so first we're going to do it using a bunch of coordinates. So number 1, all we are checking for here is, are these things functions? So all we have to do is check, does each input have exactly one output? So think of the first number in each coordinate as the x or the person, and the second number as the y. So we have xy, 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 a whole bunch of xy's. So if all of the x's are individual people, we have person 0, person 1, person 4, sorry, 0, 2, 4, 6, and 7. Okay, those are all our people. And we want to make sure that each of those people only has one birthday. Well, 0's birthday is 1, 2's birthday is 3, 4's birthday is 5, 6's birthday is 7, and 7's birthday is 8. That's all good. Each x value had its own y value, and we did not use any of those x values twice. So we're going to say that yes, this is a function. All right, for number 2, so we're going to look down a little bit. It says that we have 0 going to 1. So 0's birthday is 1. 2's birthday is 3. 4's birthday is 5. 6's birthday is 7. So far, so good. Everyone there had their own birthday. But then look what happens. We have that 2's birthday is 8. Well, if we look back, we said here that 2's birthday is 3, and now we're saying that 2's birthday is 8. So 2 has more than one birthday, or more than one output in this case. So since 2 has more than one output, we're going to say that this is not a function. Okay, we cannot have one x value or one input going to 2 or more outputs. It has to only have one birthday. So now keep that in mind, because number 3, I'm going to trick you just a little bit, hopefully. For number 3, we have 0's birthday is 1, 2's birthday is 3, 4's birthday is 5, 6's birthday is 7, and 4's birthday is 5. So now you should have thought, hey, 4's birthday is 5, and then we did that again. Well, you just said that we can't have the same input go to more than one output, but notice that they're not going to different places. All we did was repeat ourselves. And so since these are the same, okay, that means that 4 still only has one birthday. For some reason, we said it twice, but it still is the same birthday. All right, and so we can go ahead and say that this is a function still, because even though the 4 showed up twice, it went to the same place both times. All right, and then for number 4, we have that 0's birthday is 1, 2's birthday is 1, 4's birthday is 1, and 6's birthday is 1. That might seem weird that we have all these same ones here, but that just means that all of these numbers, 0, 2, 4, and 6, have the same birthday. Okay, so 0, 2, 4, and 6 have the same birthday. And that's okay. Okay, because you can have friends in real life that have the same birthday as you, right? And so we're going to say again that this is a function. So the only thing that breaks it is if you have one person with multiple different birthdays. All right, so now visually, we have graphs. And we have what's called the vertical line test, where we can check if these are functions or not by simply just drawing a vertical line. And so watch this. On the iPad, it's nice and clean. I can draw a straight vertical line, and then I can actually take it and just drag it over this graph. And notice that it never touches the graph in more than one spot at a time. So no matter where I put this on here, every x value only has one y value, so this line never touches it twice. And so I can go ahead and say that this is a function. But now we're going to see what happens when it's not. So if I take this to number 6, notice same vertical line. When I start to go over the graph, notice that it's touching the graph in 2 places. Okay, we're touching up here at -5, 0, and we're also touching down here at the bottom of the graph. And you might be thinking, well, if you just move the line over to here at the vertex of this graph, then it's only going to touch it once. But we only have to find one issue in order to break the rule. So because we found an issue right here, where this is touching the graph twice, this is going to be not a function. Okay, so not a function. So now you should be asking yourself, how is this the same as what happened in number 2? Why is what we just did equivalent to looking to see if an input has more than one output? Well, notice I labeled the dot at the top -5, 0. This dot at the bottom right here is also an x value of -5 because they're right on top of each other. So they share the same input. And the y value, we don't know for sure, but it might be something like -10 because you can see it's pretty low. But notice, same x value, -5 and -5, but different y values, 0 and -10. So what the vertical line test is actually doing is exactly the same as what we did for numbers 1 through 4. It's checking to see if any x value goes to more than one y value by checking if points are right on top of each other or not. If you have 2 points on a graph that are above and below each other, that means that one input is going to multiple outputs. And so this is not allowed, not a function. All right, if we use that same vertical line over on number 7, it's never going to hit it more than once. And so number 7 is, in fact, a function. All right, so now what do you do if you don't know what the graph looks like? Well, we have graphing calculators, luckily. And so for numbers 8, 9, and 10, all we're going to do is graph these real quick using a calculator. And then we're going to draw a rough sketch and say if it is a function or not. So first one is y equals 3x minus 1. If I just type in 3x minus 1, notice this graph is a straight line. Okay, this is a linear function. We're going to learn more about the names of functions a little bit later. But this is a linear function, a straight line. And so if I just want to roughly sketch it, it's a line going up and to the right. And this is going to pass the vertical line test. So this is a function. All right, next one. We have y equals x cubed minus 2. So x to the power 3 minus 2. This is a cubic function. Notice it kind of squiggles in the middle. It starts at the bottom, goes up, bends, and then goes up again. So if I draw a rough sketch, something like that. And notice again that this is going to pass the vertical line test. So this is a function because if I put a vertical line on it, it's never going to touch that graph in more than one spot. All right, and the last one is x equals 5. Sorry, that's covered up, but it's x equals 5. If I type in x equals 5, that is a vertical line, you can see, and that vertical line is not a function. Notice that if I tried to put a vertical line on top of it, it would just be right on top of it. It would touch it in infinitely many spots. So definitely more than one spot. And so a vertical line like this, so whenever you have x equals a number, it's a vertical line. This is not a function. All right, that is not going to pass the vertical line test. All right, so we know what a function is now. Now we have to talk about notation, which is the way we write things down. So to write a function in function notation, we're going to replace the letter y with f parentheses x, like that. And this is read f of x, where f is the name of the function. So if you look down below at the examples, we have f of x, g of x, and h of x. So we can name functions using any letter, f, g, h, k, whatever you want to call it. All right, but we generally default to f for function. And so we call it f of x, where we're going to evaluate the function f for the value x. This just means that we're going to plug whatever the x value is into the function. And so f of x tells us what the function is and what we want to plug into it. So we're going to see down below that we can replace x with anything and then get a value. So when x is replaced by a number, that number gets substituted or plugged in to the function. So down below, we're going to do a couple examples. Number 11 says find f of 4. So what we want to do first is just write down f of x. So f of x was the function on the left, negative 2x plus 5. So now we're going to evaluate the function f at 4, meaning we're going to replace the x in the f of x with the number 4. So notice the letter x right there just got replaced with 4. So I'm going to do the exact same thing in the function itself. I'm going to replace the letter x with a 4 in parentheses, because remember, you always use parentheses when plugging in to make sure you don't lose any meaning. We don't want that to say negative 24. We want it to be negative 2 times 4. And then now we just reduce this to a number. So negative 2 times 4 is negative 8, plus 5 gives us negative 3. Okay, for number 12, we want to do g of negative 1. So we start by just writing down what g of x is. which is 3x squared minus 1. You can, of course, skip that step if you can see the function easily already enough, but it's good for teaching purposes to rewrite it. Then we're going to replace the letter x with the number -1. So I replace x in the function notation with a -1, and then anywhere I see an x, I also replace it with a -1 in parentheses. So instead of 3x squared, it's 3 times -1 squared, and then minus 1. And then all you do is simplify. So -1 squared is +1 times 3 is 3, and 3 minus 1 gives us 2. All right, so now I got a you try one. Try to take h of x and plug 12 into it. Go ahead and pause the video if you haven't done so to practice already. All right, hopefully you paused and gave that a try. So what we're going to do is take h of x, which is x plus 4, and we're just going to substitute in 12 for that x value. So wherever I see an x in the function, I'm going to write a 12 in parentheses in its place. In this case, those parentheses don't do much, but it's still good practice to always write the parentheses when substituting. And so now we just have to do 12 plus 4, which is 16. So quick summary, we had that f of 4 is -3, g of -1 is 2, and h of 12 is 16. So all we were doing was plugging numbers in. All right, so now we have a little bit of algebraic notation to work with. So we can do different operations with functions. So if you have multiple functions, they can interact with each other in pretty much any way you want them to. So here are the 4 most normal or most common ones that we end up doing, where we either add, subtract, multiply, or divide functions. So the same operations we do with normal numbers. So the notation works pretty simply. If we have f plus g of x, okay, that's the way this part up here is said, f plus g of x, this is the same thing as f of x plus g of x. So the left notation is just shorthand for the middle notation there, f of x plus g of x. And this just means to add the functions. So that's a plus sign there. F minus g of x is just f of x minus g of x. So all we're going to do is subtract the functions. F times g of x is f of x multiplied by g of x. So we're going to multiply those two functions. And the last one comes with one little caveat. F over g of x is f of x divided by g of x. So we're going to divide the functions. But when we divide, we always have to make this note that g of x is not allowed to be 0 because g of x right here is in the denominator. So we cannot let that denominator be 0. We don't have to do any special work to avoid it. We just need to make a note whenever we divide things of what x is not allowed to be. Because if x is that number, then we would divide by 0, which makes things undefined. All right, so just a little bit of practice here. Number 13, we have f plus g of x. So this is equivalent to saying f of x plus g of x. So all we have to do is take the two individual functions, which I'm going to make f of x blue here, and I'm going to make g of x red. And all we have to do is add these together. So I'm going to replace f of x with the entire function, 4x minus 3. And I'm going to replace g of x with its entire function, 2x cubed plus 5. And then all I'm going to do is combine like terms and simplify this expression. So since all we have is some addition and subtraction, no multiplication going on, this becomes 2x cubed plus 4x plus 2, where the only actual things I had to combine were -3 and 5, gave me this +2 at the back. And then notice I wrote it in descending order, or standard form for a polynomial. Okay, number 14, we have fg of x. So this is the same as f of x multiplied by g of x. So we're going to rewrite it in the exact same fashion, but instead of addition, we're going to be multiplying. So 4x minus 3 multiplied by 2x cubed plus 5. And then all we have to do is a little bit of distribution. So if I multiply 4x times 2x cubed, that gives me 8x to the 4th. 4x times 5 is 20x. -3 times 2x cubed is -6x cubed. And -3 times 5 is -15. So then just writing this in descending order, we have 8x to the 4th minus 6x cubed plus 20x minus 15. Not too much to it, just multiplication there. All right, so now I have a you try one. Go ahead and try to do f minus g of x. And if you can, with the video paused, go ahead and try 1516 and the other you try, where all we're going to do is the same steps, but then we're going to plug in a number. So if you're already ahead of the game, feel free to pause and try all four there. All right, hopefully you gave these a try. So next one is f minus g of x. So that's f of x minus g of x. And notice that the only difference between this one and number 13 is it's subtraction instead of addition. So depending on how lazy you are, you might just look at number 13 and go, ah, well, why don't I just copy paste that middle line and then switch out the addition for subtraction, which is what I just did there. And I don't want to confuse you. So the only reason I did that just now is not actually that I'm lazy, but I want to show you how similar these problems are. Okay, all we had to do was change out subtraction for addition. That's it. It's the only difference between this one and number 13. So I replaced a plus sign with a minus sign, but everything else about what's going on stays the same. All right, so now all we need to do is some subtraction. So we're going to get negative 2x cubed, positive 4x, and then negative 3 minus 5 is going to be negative 8 this time, instead of the positive 2 like we had before. All right, number 15. The only thing that's going to change is now we're plugging in a 4 for the x. So g plus f of 4 is the same thing as either of these two things. You can either think that it's g of x plus f of x, and then this vertical line here means to evaluate it at x equals 4. That's the harder way of thinking about it. Okay, so you're allowed to do g plus f and then plug 4 in. But instead of that, what we can do is plug the 4 into each function individually. So we can think of this as g of 4 plus f of 4. Because notice in the notation we had before, in number 13, right above it, f plus g of x meant f of x plus g of x. So if we just replace the x everywhere with the number 4, it's f of 4 plus g of 4. In this case, the g and the f are in the other order, so g of 4 plus f of 4, but it's the same thing. We're just taking the functions and plugging 4 in for that letter x. So for g of 4, all I have to do is take the function g and plug 4 in. So we are going to have 2 4 cubed plus 5, where all I did was replace the x in the x cubed with a 4. And then we're going to add to that our f function with 4 plugged in. So that's 4 times 4 minus 3, where again, I just replaced the x with a 4. We do some simplification here. 4 cubed is actually kind of a big number. That's 64. And 64 times 2 is going to be 128, plus 5 is going to be 133. So that first set of parentheses is 133. And the second set, 4 times 4 is 16, minus 3 is 13. So we're going to do plus 13. And if we add those together, we get 146. You're always more than welcome to check these answers on a calculator, but we should be able to do that math just right here on the paper, even if you have to write a couple extra steps. Okay, number 16, we have g minus f of negative 3. So same idea as number 15, except we're plugging in a negative 3 this time and doing subtraction. So we have g of negative 3 minus f of negative 3 is what that notation means. And if we go ahead and plug in negative 3 to each of these functions, we're going to have 2 times negative 3 cubed plus 5. And we're going to be subtracting our f function with negative 3 plugged in. So 4 times negative 3 minus 3. All right, we can work this all out now. Negative 3 cubed is negative 27, times 2 is negative 54, and plus 5 is positive 49. And we're going to be subtracting. 4 times negative 3 is negative 12, minus 3 is negative 15. So we have 49 minus, 49. No, that should be negative 49 over there. My bad. So we have negative 49 minus negative 15, which is the same thing as negative 49 plus 15. And so that's going to be negative 34. Because when we add the 15, the negative 49 gets less negative. All right, if you haven't paused it yet, go ahead and try the you try one over there, g over f of 1. Okay, hopefully you paused and gave it a try. So this means to do g of 1 divided by f of 1. And if we plug in our components, g of 1 is, don't need the parentheses this time, it's 2 times 1 cubed plus 5. And in the denominator, we have f of 1, which is 4 times 1 minus 3. So if we do a little simplification here, on top, 1 cubed is just 1, and 1 times 2 is 2. So 2 plus 5 gives us 7 on top. And on bottom, we have 4 minus 3, which is 1. So we can just write that as just plain old 7. We don't need that 1 in the denominator. All right, that was fun. We actually got to do some algebra there, so that was a good time. Let's go ahead and move on now to composition. So what we just did was basic operations with functions, addition, subtraction, multiplication, division. Now we're going to do composition of functions, where the composition of two functions means to plug one function or a function's value into the other function. Okay, so to find the composition of two functions means to plug one function or function value into another. So now, how are you going to know which one to plug into which? Like, what's the context going on here? So we have the notation f compose g of x, where that circle in the middle there, okay, this symbol right here is an open circle, okay, open circle, not a closed dot like multiplication, open circle. That means composition. But you will pretty much never see me use that symbol, okay? Instead, we're going to be writing it as f of g of x with parentheses like that. And I want you to notice that the only thing different between them is in the first one, just imagine instead of that open circle, if I put parentheses around g of x like that, and I got rid of the open circle, these become the same notation. All right, so all you have to do is think of the g of x as being inside of the f of x. And these are both going to be read, or they're both asking you to plug in g of x to f of x. So notice the second notation right here, f of g of x. This looks like f of x, but we replace that red x right there with the entire function g of x. So instead of just plugging in the letter x, we're plugging in an entire function g of x to its place. And we can say both of these as f of g of x. All right, so a couple ways that this notation can end up looking. So down below, reading the problems. To find g composed at f of x means to plug f of x into g of x. Okay, so whenever we have this second one here, f of x, we're taking that and we're plugging it into the first one, which is g. Second one, p composed r of 2 means to find r of 2 and plug it into p of x. So we're going to find the second part first. We're going to find r of 2, and then we're just going to put it into p, whatever that result is. Next one, q of n of 5 means to take n of 5 and plug it into q of x. And the last one, h of j of x means to plug j of x into h of x. So a few different ways we can do this. All the notation really means the same thing. You're just plugging the second thing written down into the first thing. And it is, even amongst mathematicians, we argue quite a bit about why is this the way we wrote this notation. There are arguments on both sides, but a lot of people feel that this is written backwards and that we should put the f of x in the front and then the second function, but this is what it is, so we're all stuck with it. All right, a couple examples here. So number 17 says we're given f of x is 3x plus 4 and g of x is 7 minus 2x. We want to find f of g of x. Okay, so here's the way I do these. I start with f of x written down, where I'm just going to copy it as is, 3x plus 4. But then we don't want f of x, we want f of g of x. So if I leave myself a little bit of extra space here, so I didn't change anything there, I just left a little extra space, I'm going to replace the letter x with g of x. Okay, so instead of that letter x, I'm going to delete it real quick, and I'm going to write g of x where the x was. So now notice, it says that f of g of x is equal to 3 g of x plus 4. So now all I have to do in the next step is replace that red g of x with what g of x actually is. So the function up there for g of x is 7 minus 2x. So in parentheses, I'm just going to replace g of x with what it is, 7 minus 2x. Now if I just multiply this out to simplify, we have 3 times 7 is 21, 3 times negative 2x is negative 6x, and we have a plus 4 in the back. If I write this in standard form, this is going to be equal to negative 6x plus 25 when we add together the 21 and the 4. And so we can say that f of g of x is negative 6x plus 25. Number 18, we have an f and a g, and we are asked to find g of f of x. So because I'm asked to find g of f of x, I'm going to do the opposite of what I just did. I'm going to write down what g of x is first. So g of x equals 3 times x squared. But now instead of leaving it like that, okay, instead of leaving it as g of x equals 3x squared, which is what g of x is, I'm going to replace that letter x with f of x. Okay, so I'm going to take the f of x function over here, and I'm going to put that into g of x, and I'm going to put it in where the f or where the x was in the function. So g of f of x is equal to 3 times f of x squared. And now if I replace f of x with what it actually is, we can say that g of f of x is 3, and then parentheses, negative 2x plus 1, the whole thing squared. All right, so all we're doing is replacing that letter x with the entire function f of x. Now we have to do a little bit of squaring here, which is a little bit of work. So when we multiply out, or when we square negative 2x plus 1, the way you do this is you square the first term. So negative 2x, if you square that whole thing, is 4x squared. You multiply the first term and the second term. So negative 2x times 1 is just negative 2x, but then you multiply it by 2. So negative 4x. Then you square the last term. 1 squared is just 1. All right, so that rule I just did right there is pretty commonly used. If we have a plus b, the whole thing squared, it equals a squared plus 2ab plus b squared. Okay, very common rule we use. All right, now I just need to distribute this 3. So we're going to get 12x squared minus 12x plus 3. And that'll be our final answer there. All right, just 2 more, and then we're going to be plugging in numbers for these ones. So 19, we're given a p and an r, and we're asked to find p of r of negative 3. So the first thing I'm going to do is find this inner part, r of negative 3. The reason I didn't have to do this step in the previous ones, like f of x right here, I didn't have to do anything to find f of x, because I already had it, right? We knew what f of x was. But in this case, I don't know what r of negative 3 is yet, so I'm going to have to plug in negative 3 to r to find out. So we're going to find r of negative 3 is equal to 4 times negative 3 minus 3. And so r of negative 3 is going to be equal to negative 12 minus 3 is negative 15. Okay, so we have the inner part. We have r of negative 3. So now what we want to do to find p of r of negative 3, so p of r of negative 3 right here, all we're going to do is replace the r of negative 3 with what it actually is, which is negative 15. So we're going to find p of negative 15. And finding p of negative 15 is no different than what we did earlier in the lesson. We just replace the x in p of x with a negative 15. So this is going to be equivalent to, oops, don't need the p there, sorry. This is going to be x squared plus 1, so it's negative 15 squared plus 1. Negative 15 squared is 225, plus 1 gives us 226. And so we can say then that p of r of negative 3 is 226. All right, one more. If you haven't paused the video to give it a try yet, please do. All right, hopefully you pause. Let's finish this thing off. So given p of x is negative 5x and r of x is 3x plus 1, find r of p of 2. First thing we got to do is find p of 2, because that's the inner function. So p of 2 is going to be equal to negative 5 times 2, which is just negative 10. So now over on the right, if we want to find r of p of 2, really all we're doing is finding r of negative 10. All right, and so we can go ahead and plug negative 10 into r. It's going to be 3 times negative 10 plus 1. So that is negative 30 plus 1, which is negative 29. So we can say that r of p of 2 is actually just r of negative 10, which is negative 29. And that is the end of this one. Hopefully you guys enjoyed learning some function notation, how to do operations with functions, how to test if something is a function, and then how to compose functions. See you guys on the next one.